This video is one of a series of videos on evaluation of blast loads for structural application. In this video, we will describe the blast phenomena and how blast waves interact with solid surfaces. Additionally, we will define TNT equivalency, explore blast scaling, and ultimately go over the types of external explosions. Before watching the next videos in this series, it is crucial that you watch and comprehend this one. Let's start with the blast phenomena. An explosion is an extremely brief chemical reaction that produces hot gases and lasts barely a few milliseconds. A blast wave will occur when these gases expand tremendously, compressing the surrounding air. The blast travels due to the disequilibrium between the compressed air forming the blast and the undisturbed air in front of it. As the blast wave moves away from the explosion center, its pressure amplitude reduces, and its duration lengthens. The pressure in the tail of the explosion drops below atmospheric pressure. As a result, a negative phase, also known as the suction phase, follows the positive pulse. This figure illustrates the blast wave. The pressure surrounding the structural element is initially equal to the ambient pressure P0. When the shock front reaches the arrival time T sub A, the pressure surrounding the element increases instantaneously to a peak pressure P sub S0, from its initial value of P0, the ambient pressure. The pressure declines exponentially after reaching its peak value until it approaches the ambient pressure at T sub A plus T0. This period of time is known as the positive phase duration, which is followed by the negative or suction phase. When a blast wave encounters a solid surface, it will reflect from it. During the reflection process, energy is transferred from the wave to the surface. Due to this transferred energy, the surface will exert a force to the air local to it. By Newton's third law, the air applies the same force to the surface and the pressure is locally increased above the incident pressure. The incident wave is reinforced and reflected due to its interaction with the solid surface. The reflected pressure is to be used for design. The difference between the incident and reflected pressure in an infinite surface is shown in this illustration. The pressure that is reflected can differ significantly from the pressure that is incident, as demonstrated. This magnification may result from a number of reasons, including the structure's shape and the kind, size, weight, and distance of the explosive. The reflected pressure pulse shown in figure is typical for infinite plane reflectors. To apply for design, there will be slight modification as will be shown later in the upcoming videos. As the incident wave moves radially away from the center of the explosion, it will impact with the structure, and, as a result, the initial wave, pressure and impulse, is reinforced and reflected. When the blast wave impinges normally upon the surface, then the angle of incidence alpha of the blast wave is 0. In this case, the direction of travel is perpendicular to the surface. The point of initial contact is said to sustain the maximum, normal reflected, pressure. This is defined as face-on loading. On the other hand, when alpha equals 90, there is no reflection and the plane of structure's surface is perpendicular to the wave front. The target surface is loaded by the incident over pressure. This is referred to as side-on pressure. We now want to clarify what we mean when we talk about TNT equivalence. The trinitrotoluene, or TNT, explosive studies served as the basis for the formulas and graphs utilized to assess blast load characteristics. Information for other explosives can be obtained by relating the effective charge weight of those explosives to that of an equivalent weight of TNT. Knowing that the effects of the energy output of an explosive material of a specific shape, relative to that of TNT, of similar shape, can be expressed as function of the heat of detonation of the two materials, the equivalent weight of that explosive can be obtained according to this equation. To utilize in the equation, this table can be used to determine the heat of detonation of various explosives. Next, we will go over the concept of blast scaling. For this, the cube root law, also known as Hopkinson-Krantz law, is utilized. It states that similar blast waves are produced at identical scale distances when two explosive charges of the same explosive but of different sizes are detonated in the same atmosphere. To explain the concept further, suppose that an explosive charge of weight W and size d is located at distance r from the point of interest. It will produce at this point a blast wave of peak overpressure P, impulse I, duration T, with arrival time T sub A. If we calculate lambda, according to the cubic root shown in the equation, then according to this scaling law, a blast wave with the same peak overpressure P in similar form would be produced at this point by another explosive of size lambda d, located at distance lambda r. Furthermore, at the given point we would have impulse lambda I, duration lambda t, and arrival time lambda t sub A. It is important to note that under this formulation all distance and time parameters of a blast wave are scaled by the same factor lambda, but pressure and velocity values remain unchanged at similarly analogous times. External or unconfined explosions can be classified into three primary categories based on the weight W of the detonation, its height h, above ground, and the horizontal distance, r sub g, between the building and the explosive's ground projection. These three types are free air burst explosions, air burst explosions, and surface burst explosions. When there are free air bursts, the explosive charge explodes in midair. There is no interaction with other objects or the ground. Hence, the blast approaches the structure without prior amplification. When an air burst explosion occurs, the charge detonates in the air, causing the blast wave to spread out spherically. But in this case, the blast wave interacts with the ground first before striking the structure. Surface burst explosions occur when a charge explodes on or very close to the ground. The initial wave of explosion will interact with the ground surface to produce a reflected wave. We will go into more detail and provide examples of free air burst explosions in the upcoming video in this series. The surface burst explosions will be followed by air burst explosions in a later video. Once the three types of unconfined explosions have been comprehended, we will dedicate one video to assessing the external blast loads on structures and the blast design strategy. To proceed with this series, we need a sufficient number of likes and channel subscribers. Without your support, we can't continue with the rest of the videos. Kindly subscribe to the channel and give us a thumbs up.